So in this video, we're going to be looking at properties, the reactivity, as well as the bonding and structure of our alkanes. Now, alkanes, we already know that they're based on carbon-carbon single bonds and carbon-hydrogen bonds, and they're all going to be covalent bonds. Now, alkanes themselves, you got an example over here where you've got butane. Butane has the following formula of C4H, and then it's going to be 10, and that fits the general formula of alkanes, which is going to be CnH2n plus 2. We already know, of course, our alkanes, they're going to be our most basic type of organic compound, and we normally get them from something like crude oil and fractional distillation of that crude oil. Now, of course, alkanes, we say that they're going to be non-polar molecules. Now, the reason why we actually consider them to be non-polar is because, of course, they contain carbon-hydrogen bonds only, and carbon-hydrogen bonds, we already know that they're going to be non-polar. We've got no significant difference between the electronegativities of carbon and hydrogen. The electronegativities, the ability to attract electrons in a covalent bond for carbon and hydrogen, they're going to be very similar. Now, when it comes to our alkanes, we also say that they're going to be unreactive. There's only two reactions that our alkanes actually undergo. One of them is going to be, of course, combustion. That's why we tend to use them as fuels. And another one is going to be in free radical substitution when we use them to actually make haloalkanes. Now, there's two reasons why our alkanes are going to be unreactive. One of them is, of course, going to be that our molecules, they're going to be non-polar, and that means that they can't be attacked by nucleophiles. And another reason is that they contain carbon-carbon and carbon-hydrogen bonds, and these bonds, they're going to be very strong. So yeah, we can actually say that our carbon-carbon and carbon-hydrogen bonds, they're going to have high bond enthalpies. There's another way to describe it, and what that basically means is you need a lot of energy to break these covalent bonds. So yeah, if you were to look at our shape, our structure, and our bond rotation when it comes to our alkanes, you've already come across the shape of the molecule before, maybe in module 2, where if you were to look at each and every carbon atom, you will have, of course, 1, 2, 3, 4 bonded pairs. You've got 0 lone pairs around that carbon atom, all electron pairs repel, and that actually gives you a tetrahedral shape around each carbon atom, where you end up with a bond angle that's going to be 109.5 degrees. Now, when it comes to the shape of a molecule, right, you need to consider the shape around each carbon atom. So we've just looked at methane over here, which is going to be CH4, but if I were to take, let's say, ethane, which is going to be C2H5, we know around each carbon atom we've got 1, 2, 3, 4 bonded pairs, 0 lone pairs. Same thing with this one over here. I've got 1, 2, 3, 4 bonded pairs, 0 lone pairs. I still end up with that tetrahedral shape again. Same thing with propane as well, which has a formula of C3, and then it's going to be H8. I end up with a tetrahedral shape around this carbon, and this carbon as well. Now, alkanes, we've already said they're going to be saturated. They don't contain carbon-carbon double bonds, but a new word that we can actually use to categorize the types of covalent bonds that we can get is, of course, a sigma bond. Now, there's two types of bonds that you'll be dealing with in A-level chemistry, two types of covalent bonds. One of them is going to be a sigma bond, which of course has this symbol over here, the Greek letter sigma. And another one that you'll deal with when you look at alkenes is going to be, of course, a pi bond, where you end up with a pi symbol, of course, for that. Now, if I were to look at a sigma bond, what is the definition of a sigma bond? Well, it's when we have the end-on-end overlap of our bonding orbitals directly between our bonded atoms itself. Now, let's say if I were to look at two atoms of carbon, which you can see over here and here, what we've got over here is our p orbitals, which you can see, of course, I'm going to label over here, that's going to be my p orbitals, and these p orbitals, they will actually expand and they will actually overlap each other directly between the actual bonded atoms. So what we end up with is 2 electrons, of course, between these two atoms, directly between these two atoms, and they're going to be whizzing around. There's going to be our shared pair of electrons, and what we actually end up with is our covalent bond being formed. Now, because of course it's going to be formed directly between the atoms, we call it a sigma bond. If it was above and below our atoms, if it was a sideways overlap, we would call it a pi bond. But again, we look at that in a bit more detail when we do alkenes. Now, of course, another way you can actually form a sigma bond is between a carbon and a hydrogen atom. Now, if I were to bond these two together, the s orbital of the hydrogen and the p orbital of the carbon, they will overlap, and we would end up with 2 electrons within an actual carbon-hydrogen bond itself. Again, it's going to be directly between the atoms. Now, sigma bonds, they're very important when it comes to organic chemistry. When we deal with alkanes, they're only made up of sigma bonds, and what this means is that these carbon-carbon bonds can actually rotate in a molecule. Now, let's say if I had a molecule of propane, which has carbon 1, carbon 2, and carbon 3, this third carbon atom over here, it can actually move positions from here to here to here, and the reason why is because the carbon 1 and carbon 2 bond, the bond between those two atoms atoms that can actually rotate, and we can actually get this at different positions. So it doesn't really matter where your actual carbon atoms they're going to be attached, or where your actual groups are going to be attached when it comes to your alkanes, because of course you can actually just rotate the structure and you can end up with the same structure again and again. But this isn't actually true with alkenes, but again we'll look at that later on. So yeah, that's how we can actually form a sigma bond, and that's why sigma bonds are going to be important, because of bond rotation. So yeah, moving on then, if we were to look at our boiling and melting points when it comes to our alkanes, the first factor that's going to affect boiling and melting points is going to be the chain length. Now when we look at describing our trend in boiling and melting points when it comes to chain length, we normally say that as chain length increases, the number of carbon atoms is going to increase and the boiling and melting point increases as well. That's our description. What about if I were to explain it? Well, remember, when it comes to alkanes, they're all going to be non-polar simple covalent compounds, and of course you're going to end up with induced dipole-dipole interactions being the biggest factor that of course affects the boiling and melting point. Now let's see, if I were to compare two molecules, let's go with propane and let's go with pentane as well. If I were to look at something like propane, I need to look at two molecules next to each other, as well as with something like pentane as well. Now what we need to look out for is the number of points of surface contact between the molecules. In other words, how many induced dipole-dipole interactions we form, because the greater the surface area is going to be, the greater the surface contact between the actual molecules, and so the stronger the overall effect is going to be for our induced dipole-dipole interactions between the molecules. So yeah, if I were to look at propane, I'm just going to make up a number and I'm going to say there's 3 lots of course induced dipole-dipole interactions. Doesn't really work this way, but it helps you to visualize it. Whereas if I were to look at pentane, I end up with 1 lot over here, 2 lots over here, 3 lots over here, 4 lots over here, and then 5 lots over here. I've got 5 times the amount of induced dipole-dipole interactions compared to something like methane, whereas propane has 3 times the amount. So if you've got more points of surface contact between the molecules, we know that we end up with more induced dipole-dipole interactions between the molecules. That effect's going to be stronger, and that actually requires more energy to overcome. So again, it is just another aspect question, but in this case, the structure is going to be a simple covalent lattice structure. The bonding, if we were to look at the actual intermolecular force involved, it's going to be induced dipole-dipole interactions. The relative energy required to overcome is going to increase. We don't really talk about conductivity in this case though, but remember, you need to get the key phrase in there, which is going to be the points of surface contact between your actual molecules itself. That's how it's going to be different. Structure and bonding is going to be different when you deal with module 4. So yeah, another factor that you need to be aware of is of course isomers. Now isomers, when you deal with isomers, remember what we said for structural isomers, you've got the same molecular formula, but you've got a different structural formula. So we've got 2 molecules with the same molecular formula but different structural formula. In other words, we're going to end up with branch chains and straight chains and comparing them. Now you can see over here I've got pentane. Pentane has a formula of C5 and then it's going to be H12, and we know pentane, of course, it can have a bunch of different structural isomers, where I end up with 2-methylbutane as one, and then 2,2-dimethylpropane. Now again, what I'm going to do is I'm going to draw 2 molecules of pentane together, and you can see over here we've got very long carbon chains. We've actually got the same carbon atoms, but of course we've got a longer unbranched chain. But if I were to compare that to something like, let's say, 2-methylbutane, and I were to take 2 molecules of 2-methylbutane and stick them together, if we were to compare the points of surface contact, if I were to look at something like pentane, we've actually got quite a lot of surface contact between the actual molecules as well. We end up with stronger induced dipole-dipole interactions, and that requires more energy to overcome. Whereas if I were to compare it to something like 2-methylbutane, 2-methylbutane isn't going to have as strong induced dipole-dipole interactions between the molecules, because they can't actually pack as closely together. Now how do we actually word this in the exam? Well, we need to say the following, that the more branches there are in an isomer molecule, the lower the actual boiling point is going to be. There are less points of surface contact between the actual molecules themselves. Don't forget the between molecules bit as well. And we can say, therefore, there are weaker induced dipole-dipole interactions. Again, you need to mention between molecules, and that requires less energy to overcome. So the highest boiling point is going to be, of course, pentane out of the 3. Then it's going to be 2-methylbutane, that's only got 1 branch. And then, of course, 2,2-dimethylpropane, that's going to be the lowest boiling and melting point, because that's going to be the most branch out of the 3. So yeah, if you were to move on, I've got a task for you to do. Feel free to pause the video on this multiple choice question that's been modified ever so slightly, and then have a go, resume once you're ready to go over the answers. Just remember, if in doubt, always draw the structure out. So yeah, looking at this question then, you can see here I've got a bunch of different alkanes, and I don't know whether they're going to be isomers or not. I don't know whether they're going to have more carbon atoms or not, but of course I'm going to draw them out just to make sure that I'm getting the right answer. So we look at the first one. We've got here CH3 there, CH3 at the end there, and we've got 5 lots of CH2. So in this case, I already know that my actual formula of this is going to be 1 carbon atom, 2 carbon atom for the ends, and then I add 5. It's going to be heptane. Now if I were to draw out this structure, I've got of course 1 carbon atom at either side, and that's going to be CH3, the end of the chains, and I'm going to end up with 5 repetitive CH2s. So the first structure for A is actually going to be heptane, so I end up with 1, 2, 3 carbon atoms, 4 carbon atoms there, 5, 6, and then it's going to be 7 carbon atoms like this overall. So of course the first structure is going to be heptane. Now I'll look at the next one. That one's going to be a bit harder to draw, but I'm going to look at these 2 carbon atoms over here to begin with. I've got for B 2 carbon atoms, so I've got 1, 2 carbon atoms like this, and then I'm going to end up with 2 lots of CH3 attached to the second carbon atom, so 1 CH3 there, 1 CH3 there, and then I look at the first carbon atom. I've got 3 lots of CH3 attached, so I end up with 1 CH3 there, 1 CH3 there, and another CH3 there. Now if I were to look at the formula of this, I've got an alkane, 1, 2, 3, 4, 5, 6, 7. It's going to be an isomer of A because it's going to be heptane again, but we've actually got a branch structure. This one would actually be called 2, 2, 3, and then it's going to be trimethyl butane. We can see we've got loads of branches on here. So yeah, if I were to look at C, I've actually got over here 1 carbon atom there, and then I've got 3 lots of CH2. Now how do I tell the difference between the ending CH3 and the actual CH2s in the middle of the chain? Well, of course, if I've got CH2, I know that I must have 2 lots of hydrogen attached, and then of course a carbon chain that continues, and then we've got X lots of those as well. So yeah, in this case I've got 3 lots of CH2s there, so I'm going to have CH3 to begin with, and that's going to be bonded to 3 more carbon atoms. So I end up with 1, 2 carbon atoms there, and then I end up with 3 and then 4 carbon atoms there. I've now done my end of this chain, and then of course the 3 lots of CH2s that we've got. The next thing is I end up with another bond to a carbon atom over here, and then I've got 2 lots of CH3s attached, so 1 and then 2 over there. Technically this question is more like a structural formula understanding question applied to of course some alkanes boiling points, but of course you still need to be able to do it for 1 mark in the exam. Now of course you've got here D, that's going to be the next one. I've got over here of course we'll go with that being the first carbon atom. That's going to be number 2, that's going to be number 3, and then we'll say of course these are branches for now, even though they're not going to be branches. But yeah, I've got 1, 2, 3 carbon atoms there. On the first carbon atom I've got 2 lots of CH3, so there's 1 there, there's 2 there. On the last carbon atom I've got 2 lots of CH3, so I end up with 1 there and then 2 there. Now if I look at C and D, they're both actually going to have the same formula for heptane. They're all going to have a formula of C7 and then H16. They're all going to be isomers. A, B, C and D, they're all going to be isomers. In the case of A, I've got no branches. In the case of B, I've got 3 branches, and then if I were to look at C, I've got 1 branch over here. If I were to look at D, I've got 2 branches over here. Now remember what we said in terms of branches. The less branches you have in an isomer molecule, the greater the points of surface contact between the molecules you'll actually get, and so the stronger induced dipole-dipole interactions you'll have, which requires more energy to overcome. A has the least amount of branches, so we know of course A is going to have the highest boiling and melting point. If you were to look at the one with the most amount of branches, we actually end up with B being the most amount of branches, and of course that's going to be the lowest boiling point itself. So our correct answers for this one should actually be A and then B.